We'll let some time go by, get some people in here. But we're going to be going through some review today of Kilauea, Mauna Loa, and just some of the trends between the two. So we got data streams, photos, graphics, all kinds of interesting stuff to share today. But yeah, we'll just wait a second, then do the intro and get right into it.
Yeah, the long and short of it is there's really not been anything hugely important happening that anyone needs to be worried about.
Right.
But there's lots of interesting things that we've been observing and watching and sharing, and people are interested out there, and what's happening with the volcano even during this time of non-eruption. So that'll be our focus today.
All right, so welcome everybody. We're about to get into our update. This is going to be a Mauna Loa, Kilauea, and Pahala, a little bit of Holly Mau Mau, the pond inside of it update. We're going to just go a little bit through each of these kind of quickly and try and keep it up. So without further ado, let's dive right into Mauna Loa. There we go.
All right. What are we looking at, Danny?
Right, so we're looking at the Mauna Loa summit, the caldera, and you can see some of the cones from previous eruptions in the to the left side, and it's just it's kind of hard to get up there. We were up there recently, and not to the summit itself, but close enough. And it just it's really a trip to see this kind of wide angle shot from up there. So kind of lead in with that, and anything you wanted to note about this?
Yeah, Mauna Loa summit's really, really amazing. Yeah, you guys can see how wide the caldera actually is, right? It's really too wide to capture in any regular, even wide-angle view kind of the crater. It's really super long. There are views of Mauna Loa on a webcam on the USGS site, which anyone can check out at any point in time. And there are times when you actually, depending when you look, you can even see snow in the caldera, and so that's an interesting thing to check out from time to time.
Right.
So
let's dive right into some data streams then for this.
Yeah, that's how Mauna Loa looked just this past month, and here is the data from this month as well. So the first thing to kind of see at the very top, we can just talk about as we kind of scroll down, the tilt is just showing a day and night cycle, diurnal cycle, right? So it's basically fairly flat. There's nothing to really see as far as tilt there, apart from not much is happening. As far as GPS, that's a little bit different.
Right. We've been seeing this trend follow the eruption, and we'll mark it with the pin again. So this is basically, that's a lot bigger than I wanted it to be. Stand by. Let's try that again. So right here, this is basically the 2018 eruption, and you can see the inflation had stopped at this point, and USGS lowered the alert level to green. Right in here. But following the eruption, the end of the eruption into October, we saw the pick back up of inflation. And then we went back into yellow, but that's probably way too early.
Yeah, but interesting, like right where we drew that line, there's a little bump just to the left of that.
Right.
And so there are these little variations that happen within this GPS plot, which is actually a distance between points across opposite sides of the caldera, Mauna Loa, right? So if they spread apart, in theory, magma is pushing from below and swelling, and they're spreading apart. And that's what we're seeing overall pattern of that. But with little bumps in between. So once in a while, they do kind of come back together a little bit to contract, like mostly spreading, but once in a while, it gives a little bit. And that's what that little bump actually is, right where that second arrow is on the right.
Right, and we have one of these pretty recently. It looks like something similar, and then the station goes offline.
Yeah.
So usually when you see something weird on a station and then it goes offline,
you'd be suspicious.
Be a little suspicious on that one.
So yeah, it's possible that because of recent winds that something was misaligned with the data transmission, and so we'll have to wait for them to reestablish the connection. They'll revise the data. Whatever gets posted after they correct this will be the real data.
Right.
For now, we have to kind of just wait and see. But it's possible we're seeing one of these little smaller adjustments that's going back the other way. And in itself, it doesn't mean much necessarily until we see a longer pattern and a real pattern that's greater than what we've seen in the past, these little abnormalities within a larger trend.
All right. And really, there isn't that much going on with Mauna Loa. The main thing right now is the continued seismic and the continued elevated seismic and elevated inflation. We'll show the elevated seismic here in a second. Now you can see in this little graph how we have all these trends, and this was increased activity in yellow Mauna Loa from 2014, 2017, 2018. I'm going to get rid of that giant line.
Right. So yeah, that we're looking at is the dark blue boxes, right? And like they're basically probably a couple week period at a time, something like that. And the height of it is how many earthquakes are happening within that amount of time, right?
Right. So you get these trends over long periods, and you can kind of keep track. You get some anomalies like this little guy, but you can see the general trend coming up, coming down. But then in these last few months, falling, and right about here's the end of the 2018 eruption, maybe a little earlier, but yeah, right in there. And then you just see this elevated trend of seismic, and that's continued for months now.
Yeah,
Almost
right,
a year
yeah.
that's been going on.
Yeah, so earthquakes are so elevated underneath Mauna Loa, fairly shallow underground, in an area where the magma is building very slowly. There's nothing to be concerned about yet. Magma's filled that volcano for a lot of time, and a lot of times it doesn't actually feed anything. So we have to wait for actually signs that's going to come out of the ground, and we're on a lookout for that, of course. One thing to note on this graph we're looking at, the very, very right bar of the graph is something you have to ignore because it hasn't fully captured the full amount of time, right? Just something we mentioned before. We're going to mention that again. So, there is definitely an increased trend. One thing that's noteworthy to me is when you read the Mauna Loa update, now being put out every week by the USGS,
Right.
we see that one of the first things they mention is how many earthquakes, more or less, are happening underneath the summit at any point in time. So this past week they mentioned there were 49 earthquakes, small magnitude earthquakes, all smaller than 2.5 magnitude. At intermediate depths, shallow, less than 6 miles below ground level. So, that's kind of what we're looking at.
It's continuing, basically.
We've seen, it might have been a month ago, something like 130 might have been the weekly report.
Right.
So, that's the variation we're dealing with right now. So, relatively speaking, 50 earthquakes is not as many as we've had even within the last couple months. But even if we're at 130, we would want to see it climbing more and more and more. And for kind of comparison, before an eruption, we're expecting something like thousands of earthquakes per hour.
Right.
Right. So, a few hundred per month is not quite there yet. It is elevated above background, but it's not building to the point of cracking to erupt out of the ground quite yet.
Right. And we also had this November flurry of earthquakes where it looked like something maybe doing something, but it kind of died back off, and you can get these high anomaly points, and even those are expected.
Right, there's a lot of noise.
A lot of noise.
And not to call out noise and say that's insignificant and meaningless, because maybe those are the signs of the thing we're reawakening, or transition times and times of changing from more activity to less activity. Right. It's hard to tell exactly. I just call it noise because we can't say conclusively what any of those things actually are, and they're kind of outside of the regular pattern, which is more what we're concerned with at this point in time.
Right, the established trends. All right, so from here, let's look at one of the main questions we've been getting recently is about the earthquakes going down at Pahala.
That's right.
Deep earthquakes, so we wanted to take a little bit of time to address some of those.
Right. So the first thing to mention is the depth of those earthquakes in Pahala. While Dan pulls up the earthquakes, we'll look at the kind of the depths of those. And we're talking generally about 30K to 40K down, more or less. We're talking, that's the range of maybe a little under 20 miles to 25 miles or so, something like that.
Right.
Underground. So it's really far down there. It's about as far from Kilauea's summit as Mauna Loa's summit, right? And so when we talk about these earthquakes, I don't necessarily want to link them just to one volcano necessarily, but also we don't know how it really connects is kind of what we're going to get at here, right? Those earthquakes are not connected in any conclusive way to what's happening at the surface of either volcano or anywhere else on the island. So what Dane's got up here is a plot. I think he's got the last 7 days. Is that correct, Dane? Or what have you got?
Yeah, this is the last 7 days here down in Pahala, and you can see two different markings here. Mm-hmm. You can see the circles, which are deep earthquakes. You can tell by just the depth. Mm-hmm. So the deep Pahala earthquakes, these ones are called. But then you can see these little diamonds.
Yeah, it's really hard to see.
They're little, it's really hard to see, but there are little diamonds in here, and there's the deep tremors.
Right.
Down behind below Pahala as well.
Right. So if you're ever actually looking at a seismograph, which is the actual plot of a seismometer, when the wiggles is drawing on a paper, these signals, these earthquakes, have different shapes to them. And so the reason is how the energy is getting released. A normal earthquake is actually something physical, a solid rock breaking, right? Magma itself as a liquid cannot produce an earthquake directly because it can't break. It has to actually exert pressure on the solid rocks around it and cause them to break. And that's when you can have an actual decent, relatively normal earthquake, as we have kind of pointed out here as a deep earthquake, as the bottom trend right there, right? The middle plot, the kind of sausage-shaped one, this red and deep tremor, that's what we're talking about as far as tremor earthquakes, right? And the equivalent that I think of is a fluid going through a small opening and vibrating the walls of it. Like when I think of this, my first image in my mind is playing like a recorder. I had recorder lessons when I was in elementary school kid, and maybe lots of people did. And when you blow that air through that little tube, the air vibrates back and forth. In that case, you can hear the actual vibration of it. It's producing a sound, right? And so these frequencies are lower than we can hear, but it's that same kind of vibration of the fluid moving through a narrow area. And the vibration, the harmonic is traveling through the earth from that, right? So those are areas that you'd expect to kind of stay fairly constant as far as where that happens, because that conduit, in theory, is not moving every year, right? Maybe it moves over geologic time, but it's not happening year to year, right? So the interesting thing is that if you look at where these earthquakes, like where the tremor and the deep earthquakes happen, they're slightly offset. And there's a third kind of event, which is the shallow long period. And shallow long period is also kind of a vibration event, but it's happening from shallower, and in this case, they're calling it shallow, a distinction within the structure of Kilauea volcano in this particular case.
Right. This is more of a, these are shallow, above 10 kilometers, basically, events.
Right. Whereas the deep ones are kind of at the base below Kilauea volcano, not even inside of it.
Exactly. On
the way there and possibly elsewhere, but impossible to tell.
Right.
Right. So, yeah. So there's a really interesting this plot, and there's a map we also have that comes from this paper. That's by Wes Thalen and Aaron. I forgot his name. Aaron Wetch.
Right.
Right. AVO, Alaskan Volcano Observatory, and they've basically tried to untangle this giant mess of data, and it's not easy, and it's very inconclusive, right? But we can kind of show you guys like what they propose as the most logical way of understanding what's happening right now.
So we have a bunch of different, from what we know just in the past year of watching these quakes down Pahala area, is you have flurries of quake activity down there, and it's seemingly random, and it doesn't seem to correlate to anything else shallower, following up afterwards, at least in the ones we've seen so far. And then this paper, it goes way back. So we were just looking at the past few years. These guys are looking at the past few decades.
That's right. I think a very important point, right? So, this is going on a long time. And to date, there is no predictable consequence of these flurries of deep Pahala earthquakes. So a lot of us like to think, we're seeing something happening on a monitoring stream, and so this must mean something's going to happen at the summit of Kilauea, or we've heard at the summit of Mauna Loa, or something else, other ideas people might actually have. But this is one of the cases where we just don't know enough to really say that this means anything about anything. So it's interesting, we see magma is coming into the volcano. The volcano is still alive. We can't actually see it coming in from that area into Kilauea. But we presume it must happen because we still see earthquakes happening underneath in the shallow area of Kilauea, right? And adjustments in Kilauea. That's kind of all we've been talking about for the past many months. But now we're kind of seeing a little bit of life from the actual source. But the issue is that magma itself, being liquid, doesn't produce earthquakes. It has to actually go through a narrow spot or push something out of the way for that thing to actually crack and break and make an earthquake or show a vibration. So a lot of the pathway is aseismic. That means having no seismicity. There are no earthquakes, and so you just can't get that information from here. And there's not many other ways to look that far deep underground and separate everything happening above it from what's happening below that and say, okay, right at this depth, here's what's going on with the structure of it. That's why it's so basically at this point impossible to really say that these mean anything predictable as far as what Kilauea might do or Mauna Loa might do or anything else, really. It's interesting and unusual, but we can't say anything beyond that of where we're going to go with this. So it's kind of, we've had a lot of these questions. It's not directly related to Mauna Loa. It's not directly related to Kilauea. It's related, if anything, to the hotspot plume itself.
You're not going to track magma movement up to the summit from Pahala.
It can't come straight up under the ground from where it is through Pahala itself even. It's 25 miles underground there. It has to go through the pathway that exists already under either through Kilauea or through Mauna Loa. It can't come out through the Southwest Rift directly through there. And that's why it has to. It's a lot easier to go through the established pathway, even if it's circuitous and going back and forth weaving, than to come through solid rock 25 miles up.
Yep.
That's not going to happen that way, right? So anyone in Kau area, you can kind of rest easy. Nothing's going to happen right there from this kind of flurry of events volcanically anytime soon right there, right? Kau is under its own interesting geotectonic setting between Mauna Loa and Kilauea. We'll address this in much more detail as time goes on. Maybe we kind of leave it at that for now, but we can kind of just say that the Pahala earthquakes are not directly connected to Mauna Loa or to Kilauea.
Right, and one interesting thing is about just the depth of these earthquakes and the depth of the mantle fault zone. And that's kind of where this relationship gets inferred,
Right.
especially in these papers. It's just way too coincidental for these things to be at the same depth and for there not to be any interaction there between them.
Right, right. Yeah, so this diagram is really awesome because the top panel, is actually the real data. And every little dot on there is an earthquake, right? So, you can see like the mass under the right side of the graph. Maybe I can...
Yeah.
Let's see, where's my mouse? Over here? My right spot, okay.
Are you trying to draw?
Yeah, I guess I need to push the draw button first. All right, guys, I gotta get my Madden glove. Here we go. So this bulge right here, that's what we've been talking about for most of our era, right? This is all the Kilauea structure and edifice right there, right? All this blob right there, right? Okay, so let's ignore all of that. That's all the shallow. They've drawn down here as a shallow LPs. Now, all these deep earthquakes, the deep tremors, all these squares, yellow squares over in here, right? And there's also another category down here that's kind of a particular depth with a little gap in between, right? You guys can kind of see how there's very distinct lineations, right, of where earthquakes happen, right? So this is down here, the bottom panel is how they interpret this data above it. So you can see that they're considering all these earthquakes down here at the bottom of the plot to be part of the mantle plume affecting the base of the plate, right? Deep tremors happening where that plume perhaps intersects this very distinct lateral sideways mantle fault zone, right? You guys can see this very distinct line right across, right above there, right? And clear room, delete button. Okay, there it is. So what we really see is there's pressure here. There's pressure here, and that's likely where magma is moving. We can see kind of the long period signal.
Right.
In between, something's got to connect these things. And so the best idea we have now is the magma is actually using this fault zone and somehow getting through here. Somehow, because no one really knows.
Yeah, nobody really knows.
Right.
That's the easiest
right.
explanation. Just
but it's
to go
key
to
to me to understand that these little dots in the area right here, these are not tremor earthquakes. This is a regular fault earthquake. It's a regular fault zone, a regular solid rock moving. Now, the magma moving through there is possibly can either create some lubrication, it can create some pressure to actually push this thing and actually cause it to slide to the side. That's kind of a big unknown. That's what we really don't know how that actually all goes. But that's why this diagram is so interesting to me, and I can kind of leave it at that. And this may actually bring out more questions and answers, but that's where we are in a science at this point, and that's okay. And that's how those earthquakes fit into the pattern of Kilauea and Mauna Loa. So I'm kind of tie it together. Any earthquakes happening down in this zone of these little yellow squares to actually reach sideways those 30 miles and up another 20 miles. That's a long way for it to go. And if that happens, it's not going to happen in a period of days, right? Yeah. It's not might not happen in weeks, might happen in months. It's hard to tell exactly when it gets there, and who knows how many in between pit stops it's going to take.
Right, and then there's just so many dynamics on Kilauea, which we'll get into when we get into the Kilauea update, mainly regarding the South Flank movement when we try and talk about shallowing of magma at Kilauea.
Yeah.
So there's just so many dynamics about it, and this Pahala thing seems to be a standalone, unique event, unique situation there, where it's just hard to infer from other elsewhere. And these earthquakes just go back long time, the records on these deep Pahala quakes. So with that, I think we can transition to Kilauea.
Yeah.
Want to do the update first, or want to talk about the pond?
Yeah. Well, let's look at the signals first, because I think the pond's more interesting. We can kind of go through this a little more quickly, right? So,
right
on Kilauea, there's not a whole lot happening different geophysically. Kind of the patterns are still there. You guys can see on a GPS plot across the caldera, Wekahuna to Crater Rim, which are shown here. We've mentioned that there's a little bit of a slightly steeper slope in a recent couple months, but that's kind of continuing still, right? Kind of the right end of that is a little steeper than the left end. But right there, right before that, right next to the arrow that Dana is drawing, you can see there's a little excursion, right? Like a series of points kind of clustered just below the main side of the line. and then it jumps back up again.
Right.
And that was interesting because it didn't seem to be one single data point out of the way, right? There's probably, I don't know, 5 or more data points within that little range right there. And it also corresponded in time to a series of earthquakes at Kilauea Summit.
Right.
And earthquakes that were reported as being unusual and how they were felt by people in Volcano Village in particular. So we've pulled up some of the earthquakes from that week, right? It seems like there's still earthquakes happening there. I think there was one even yesterday in that same kind of area. But they kind of start off around the 2nd of September, maybe. It's in the beginning of the month or so.
Right.
And 2nd, 3rd, 4th was when this main event was actually happening.
So one of the interesting things is in that earthquake, we looked at each of these stations to see how they individually moved. And the cross caldera data we were just looking at measures the distance between this guy and this guy, right? So in that quake, UWEV moved a little bit to the northwest, just a little bit, and then also a little bit vertical, this touch. We're talking very small, but that was the movement. And then Krim was the other one, just moved a little bit east. And we're just, small movements, but...
Yeah, small adjustments, and it's hard to say conclusively how those fit into a larger pattern of what's getting pushed or pulled in what direction, because as we've kind of been dealing with for a long time, even early on in the East Rift Zone, just because we see a pattern of spreading and even something sinking doesn't mean that the thing is necessarily either deflating or inflating, because it can do either one and have a similar surface expression. You need more information than that, right? So it's kind of interesting to see that was adjusting. But when I was looking at these earthquake patterns, what I noticed right away and draw on a map is that line right there that Dana's drawing, right? Most of those earthquakes fall pretty close to that line, and those are the ones that were coincident with that excursion on the GPS, and the ones that were felt in Volcano, as people described them being a circular rocking motion kind of thing, right?
Weird comparatively. And these are people that went through the eruption last year and
all the different collapses.
Yeah, maybe some of the most... in terms of experience, the most veteran residents for earthquakes in the world, because these guys are, at least in terms of recent, they got just rocked last year, rocked. So to hear them, people up there say, "Oh yeah, it was different, it was weird." Right. Okay, now you start listening.
But what's really interesting is that every fault has a different kind of dynamics and characteristics, and even over time they can behave differently depending on what pressures are being put upon them, right? So. In this particular case, that line of, these earthquakes actually fall fairly close to a line. Normally you have to do more work to get them to look so pretty, but in this case it looks like they're actually matching this collapse line, which exists that matches the edge of the collapse pit that formed last year.
Right.
It's a little bit too neat. And if you look at that, where this line faces, it faces right towards Volcano Village. So if you can imagine, the north half of Volcano Village is feeling a different motion initially than the south part of Volcano Village. And if you happen to be somewhere nearby, you might actually feel one and the other, back and forth, or forth and back. And that can start creating some of that weird effect. Yeah, not only that, this fault line at the summit is likely curved, right? It probably actually curves back around.
Just somewhere.
Like that. Yeah, exactly. Because Kilauea is within the caldera itself. So actually a pretty good job.
Yeah.
It actually goes around
a little bit wider.
Yeah, a little bit wider right there, yeah. But that's the main structure of collapse of Kilauea caldera going back about 500, 600 years. Right? So likely that fault kind of curves. So if you imagine a fault also curved and that motion is happening, whether it's down or up or sideways, whatever, the thing broke and it's adjusting slightly to the side, then you can have a lot of weird motion, especially being one, that close to it, two, right along a direction of where one side's going to move different from the other, right? And then on top of that, you're kind of probably a little jumpier, and you're looking at you're feeling how it felt, and it's not so simple a thing as we've all kind of experienced with earthquakes. We all have different personal stories of how we feel them or don't feel them, or when we feel them, or when they wake us or don't, or whose house we're at, whether the house shakes more or less, or facing this way or that way. So all that kind of stuff varies.
Yeah, definitely. So that quake was an interesting one for a lot of people to go through again.
The largest one I want to mention was a 3.2.
Yep, it was this little guy right here with a pretty shallow depth above sea level.
Yeah, above sea level, yeah. And it was on the 6th, 7th.
The 6th.
It was the 6th local time.
Yep.
Evening of the 6th.
Yep. So, yeah, and other than that, seismicity-wise, South Flank remains with a decent amount of earthquakes, scattered between it.
A little bit
There's
light,
a little bit
but
light,
still,
but
it's still
there.
happening.
Yep, still there. GPS shows south flank still moving.
We can pull up the GPS a little bit. Yeah, we kind of see that, the patterns haven't really changed a whole lot.
Right.
There is a little bit of question about what's happening at the right end of these graphs as usual, but like that's kind of always a suspect, and our eyes plays tricks on us in the last couple of weeks, right? So maybe there's something happening in the last few data points coming in, but it's nothing conclusive yet, nothing dramatically, imminently urgent that...
And basically the GPS, we've learned the hard way, don't start looking at right at the edge, right where the last data points, it really does give you some tricks.
Yeah.
The GPS is much better over long periods of time. And whereas like tilt meters, which we're not really going to go into because they are more dealt with when we know magma is coming. But the one thing that the tilt meters have shown us recently is there's still DI events at Kilauea Summit, which is, maybe you would want to go into that distinction, why that's important to be able to see that type of thing.
So there are still deflation events. If we look at the signal for Kilauea Summit, mostly what you see is the offset of that earthquake that happened last week, because the ground did move quite a bit and there was an offset, and I think we need
this guy.
We need I don't know if it's on this page. We need both a summer camp. Yeah, I mean it's basically this guy, but it's showing as 2 lines instead of a single one as it does in USGS science. So that big green spike in the middle, that's the jump, I believe.
Right here.
Yeah.
Oh God.
Yeah, it's kind of hard. Yeah, why don't we go to the USGS page and let's look at that plot, because it might look a little cleaner. All right, so you guys can follow our click through to see how we get the data. All right, this is the one I'm looking for here. Yeah.
Oh, UWE.
UWE. Yeah. Okay, so. All right, so mostly what you see, the blue line is a summit, the green line is a rift zone at pool, right? So there is, some increase in the line of pool, but it's kind of long and steady, and we don't know if that's just drift or what else is happening there.
It's tilt.
There's no other signals of anything happening to collaborate that actually being magma. That's the same as it was before. At the summit, what you basically see is that big offset of spike, right? So right here, this zone, that's the big earthquake that happened right in the evening of the 6th. There it is right there. Before that, here's a deflation-inflation event. Afterwards, here's a deflation-inflation event. Here's another one. And they're not happening super often, but they're pretty big, right? This is like something like a 5 microradian event in there. And then, they're happening every, few weeks, every week, maybe once a week or something like that. So they're still happening. It's hard to say conclusively what that means. We've kind of been studying the deflation-inflation patterns as published during a pool eruption, and in that particular case, they noted that changes in activity usually went along with very, very few deflation-inflation events. So that when you have a lot of deflation events in the same period of time, you're less likely to kind of stay the same and nothing change.
Right.
So that's kind of where we are now, and it's hard to say anything conclusive about that, but that's kind of where I would still lean. That's just one more data set kind of leaning in that direction if it's not very conclusive.
All right, so back to the GPS, and we're continuing down. We can see there's not much change on these bad boys.
Yeah, and what we're really curious about is the slope of this line, right?
Right.
As it approaches the right end of the graph, right? So there might be some slight adjustments, but there's nothing really major happening, right? Nothing clearly as major as what was happening in a few weeks preceding the 2019 eruption, as you can see kind of at the just left of center of these plots where you see the big gap, a big break in all these lines. That's what the eruption actually looks like.
And one of the still points, this is going to be like beating a dead horse, but the south flank is moving at an elevated rate compared to prior to the 2018 eruption. As showed here, you have this line, which I just demonstrated terribly, but yeah, there's a line there somewhere. And then this line is a little bit steeper than that line.
Right. It's actually something like 4 times the slope, actually, if you calculate it. It's a little bit steeper, but it's significantly a greater amount of movement.
Yeah, so that's a big thing that changed following that magnitude 6.9 on May 4th, 2018, and it hasn't really changed since then. Like that had what got put in motion is still in motion.
That's right. That's right. And so that's what we're looking for at the right end of here, and we can't really see that little wiggle at the end really means anything, and it may be that it actually just stays the same. That's kind of, we've seen these little wiggles before in the last few months, and they've all kind of averaged out to that long, beautiful looking line by now.
Right.
So as far as South Flank goes, that's still the status quo. It's still moving very fast. Nothing's changed that, and we're still kind of waiting for, potentially more seismicity on the South Flank occurring because of that, right? We are a little bit light in earthquakes on the South Flank, not super, but...
Right, there's a chance for, a slightly bigger earthquake, and we've seen, one of those before, and we've talked about it with the magnitude, what was it, a 5.5 or 5.3, shallow about 6 kilometers down, the South Flank, movement, and we were talking about it even before it happened, like, hey, so...
Right.
The possibility for these types of quakes still exists, and there's still going to be technically some kind of aftershock from
Right.
the magnitude 6.9.
Right.
And this could continue, or most likely will continue, for months to years. That type of aftershock continuing effect until this South Flank catches. Once the South Flank catches, then okay, now we can change the conversation up a little bit about
Right.
what is the status of Kilauea. But
Right.
a lot of things that, this is happening, this is happening. It's like, did the South Flank stop moving? No, it's still moving. Okay, then what are we talking about?
Right, everything has to exist in the context of the South Flank moving.
Right.
Absolutely, yeah. Yeah, so that's where it stands with Kilauea.
All right, so now for the thing that a lot of people would want to talk about, the lake.
Pond.
Lake.
Pond. Lake, pond, big pond, okay.
Yeah, whatever. It's semantics at this point. Like, really, it's
Yeah.
however you feel like calling it.
Yeah, so I did look it up when it first popped up, and I think the definition had been, if you could see all the way down to the bottom of it, it's still a pond, and if you can't see the bottom because it's too deep, then it becomes a lake. Now,
Right.
since we have sediment and acid and other stuff dissolved in our lake, and we can't see the bottom of it, is it really actually a lake, or is it still a pond, even if it's shallow enough that we could see it if it was clear? I don't know.
Yeah, I have no idea.
So
at
we're
that
kind
point.
of being a little bit loose with our terminology here between pond and lake, but that's kind of where we're coming from this, So forgive us
It's
if
not
we
a
see-
puddle. It's no longer
Yeah.
a puddle. It has been upgraded, and then you can see the zoom in. Like you can see, it's estimated at like 7 degrees Celsius.
Yeah, look at all those ripples on the surface,
Right.
right? So there's probably gas bubbling through there, or, I suppose it could be wind, but it's more likely something coming through than affecting one small patch of the surface and not another.
Right. You do have right. Let me get the Mad Pen. All right. So in here, you have a bunch of ripples, right? But then you get this little patch where there is none. You go remove the pin, and you can just see some of how it's
Right.
not exactly uniform, even
Right.
in the ripples. So yeah, I believe wind in some of it, but not
In some parts, yeah. The other problem with wind is, of course, that pit is so far down. In a hole in the ground that how much wind can you really get? And it's got to be going down and turning right around and coming back up again afterwards to actually go anywhere.
Right.
Because otherwise, it's going to hit the wall within a few feet of there.
Right,
Right.
but that is the USGS explanation currently is the ripples are wind. Just to acknowledge that.
Yeah. Okay. Yeah. And of course, we have seen there's a lot of steam coming up through there, and right, so there could be some convection currents even locally that just occur along the surface of that pond, and
Enhance.
and we can't really see that well from elsewhere, right? So yeah, other areas that the USGS released about the pond have shown changes in its coloration, right? Kind of greenish and bluish right there, right? You can kind of see, looks like different kinds of minerals dissolved in it, and different kind of streaks in there.
Right.
So the last report we have, September 2nd, of the dimensions of this thing, I want to say it was 90 meters across east to west.
And 45 across. It's super close to a football field.
And 45,
Yeah.
north
Just
and south,
imagine
right?
now it's like the football field with the end zones, or one end zone and the sidelines. Like that's
Right.
basically the scale of this thing when we're looking at it, and we'll get a little bit of. We'll just go through this little progression real quick.
Yeah, take it away.
So we just have these USGS images from the one area that you can actually see this pond from the crater rim. Everywhere else, this thing is so far down there. I think a lot of people they underestimate how deep this thing is. People will be like, "Oh, we gotta watch out. People try and go swimming there." It's like, "Oh no, you'll die like 3 different ways trying to get down to that thing."
Yeah.
Yeah, it's way too far down. That's way too steep. That pond will scold you nice and good, like it is, Hades or something like that. It's 70 degrees Celsius down there. That'll cook you. That's poaching temperature basically.
Right.
So we have August 9th. We began in early August, late July. Like wasn't it late July the first?
Late July. I want to say maybe the 25th of
yeah,
July.
Something like that was the
when
first.
It was actually confirmed.
And then by this point, we're getting bigger. We're getting bigger, and you can just see it fill. And the scale gets a little wonky, but it's fine.
Right, they're zooming out the camera as they're taking the pictures because the lake's getting bigger and I have to zoom out to see the whole thing in there. So
right, you can see just on like this little edge, or let me get the pen up here. It's just getting a little close to that scale edge, and then by this point we're already losing part of the water there. So readjust the camera each time. Oh, and then we get to September. Still getting bigger, still hot. And it's been increasing pretty much steadily. Like, what is the latest estimate? About a little less than a meter a week.
Yeah, I haven't heard anything recently updated, but that's about what I heard. About a meter a week, or sometimes.
Right. And one thing you can see here is just this one spot where there's this discoloration on, like, every good photo that can show it from that angle will show it from that angle. Yeah, my marks moved, but. Yeah, you still see it here, still see it here. So that is an interesting area. Something's going on there, stirring. And we do know, one of the main things I like to point out is the Keller well, which is about 1 kilometer from this pool. When the samples get pulled from there, it's the same temperature as the pond water via the thermal guns. But the other interesting thing is it's not sulfuric, the water. It's not an acidic water that they pull out of the well. It has a pH about 7.
Right.
It's pretty close. So for this pool, which looks like really acidic, like, gonna remove some rust from a nail type acidic, it's fine. It comes out and it's green. It comes out and it's this. So somewhere in between, is getting this. The water is absorbing this, whatever it is, the minerals, the metal, the SO2. Right. It's happening locally.
Right. So yeah, in a few minutes we'll show you guys a cross section and kind of maybe talk about why this water is going through some sulfur area.
Right.
But before that, we can finish going through the sequence already. Sequence of images. Yeah. Okay. So we've seen all the images, and let's show this thing. This is so you guys have perhaps you've seen the USGS has released an animated GIF that kind of shows the filling of a pond. From their time-lapse camera. And so all we've done here is take that animated image and superimpose it. It's slightly distorted to kind of make it fit, but onto the wider angle view of the crater, so you can kind of get a better view of, sped up view of this pond filling over the last, it's been almost 2 months now.
Right.
It'll be 2 months next week.
And the idea is, about the coloration. Just to recap a little bit, it looks very similar to geothermal ponds, and there's other volcanic lakes that we've looked at. I can't remember. There was one in Russia we were looking at that was very similar. Color of the color of the way it looked in the pit. It would seem to be just sulfur absorption. Minerals, metals, some combination. It's some kind of volcanic cocktail in there.
Right. Yeah, and you just see this a lot in mines also, right? You see this kind of similar, areas that we deal with cleaning up nowadays as Superfund sites, for example, are areas that have been mined for a long time and have this real concentration of these acidic minerals that have this very similar color as what we're seeing in this pond over here. So likely a very hazardous place to be near, right? So
It's getting bigger and bigger. All right, so let's get into some diagrams of this bad boy.
All right, yeah, so...
Let's look at before.
Yeah.
Before the...
So first of all, I mean, we don't know much about how things look now underground, right? We're kind of going out on a limb here and really trying to provoke some questions, really, and some thought processes of what might be happening underground here. So we're starting off with a before picture, right? So kind of the upper red line is the shape of the crater after the collapse. So we're going to ignore this for now, right? The shape of the ground originally is this blue Halamaua crater is right there. The little lava lake pit overlook vent was right up here with a feeder conduit coming from this large path below, right? So this shape of the magma under here is coming from the pull-in diagram from, you guys just professional paper. All I've done is just trace it out here and kind of move the labels, right? So it's thought that we have our South Kilauea Reservoir, or a shallow reservoir, to the shallow lava lake. The East Rift Zone kind of connects through here. The Southwest Rift seismically, where magma goes through there, but also magma can come up through the reservoir and erupt in the volcanic Southwest Rift as well. So that's kind of background, and not really the focus of what I'm going to talk about now, so I'm not going to get distracted. But what we're really worried about is the water, right? So beforehand, the killer well is an area somewhere in here, and it reaches water in an area around 600 meters above sea level, right? And we know there's water there. We don't know how far that water exists towards the caldera from there, right? To the north and east from there, right? Mm-hmm. There's a big question mark right there.
And it's a single well, like the only well.
See, one single pinpoint prick through the surface of the earth that found water in one spot, right? Yep. We don't know if that was just one, for all we know, that thing could be...
We know a lot about that.
100 meters wide,
yeah,
and stuck on all sides by some fault. Oops, some noise down here. On the east side, we also have some water coming in. We don't know how far it actually goes. It's debatable how close it actually comes to the magma, right? There's magma in the reservoir down here. There's some zone of heat that exists right around this thing that the water just can't get any closer to.
Right.
And we just don't know anywhere how far that actually went. What we do know is that we have an area, Steaming Bluff, that exists along a caldera wall right up here. So there's some pathway for steam to make it up along that fault, and that's existed, and that's stayed stable and constant throughout from before to now.
Right.
Okay, so that's the before situation. That's important because when we switch to the after, we're going to have to keep that in mind. So after is even more wave our hands in the air, we're not really sure what's going on. But let's look at the water first of all. We know that at the surface, at the pond, the water has to connect, right? Let me point out right in here is where a pond is forming, right? So that water is exposed right in there. It's not quite as deep as I've drawn it in here. I've drawn it to the maximum extent it actually might get,
right? But
it has to be connecting, right? And if we're using our model of the rocks being hot, being what's preventing the magma, or the water from coming in there and actually filling the area, then it's hotter the deeper you go in the earth, pretty much everywhere all the time, and especially if there's magma anywhere around, so it's going to be hotter down, so maybe it's hotter underneath here, and maybe this water only connects at the surface, and it's hard to know how far down it actually goes. We really don't know. There's a big question mark there. Coming in from the edges, does this thing go all the way down towards the top of the magma body? How close does it get? I don't know. Question marks there as well. Could this water move into this now collapsed rubble pile that's filling part of the old reservoir? We don't know that from either side as well, right? There's a lot of question marks in here of where this water might actually be. We just don't know anything about where the water is. What we do know is this. That's the only part we know.
Yeah.
It's right in there.
There was one other thing that we do know is Keller Well, which I'm not gonna. It's somewhere over here, basically. Assume, and we know from it the depth of this is where this water line comes from. Is we're just taking the depth of that well and putting it over here and saying, hey.
Yeah, that's right. So, you want me to take over for a minute here?
Yeah.
Okay, so what I've drawn here on this kind of after the fact, besides the water, is a bunch of extra faults. All these black lines are faults, right? This is a collapse fault. The caldera, this one over here on the right side didn't move, but we have a new crater from there to there, and right here is our range. Here's our range of collapse in 2018 from there to there. Okay, so we know that this part of the new collapse is steaming today. So this fault here likely goes and reaches water as well, right? These over here is where the sulfur comes out. Sulfur comes out of here
The fumaroles.
And over here, right? Yeah, exactly, the sulfurous area, yeah. And so when we're talking about the lake actually being colored and acidic, it's in between these areas of fume coming out here and here, right? So in between there, the water is going to come up through intersect that pathway either on this side or both, and that's why it's going to actually get acidic over there.
John Madden would be proud of this one.
Yeah.
Okay.
Yeah. So there's a lot more in this diagram, but we won't have to go through all of it necessarily. But that's what the deal is with the water in particular.
Right, and the main thing about the water is just the consistent rate that it increases at, the heat that it is at, the same temperature as this Keller well. Those are kind of some really big points about helping push through this theory,
right.
Making it one of the more likely candidates for us. And that's, again, we've estimated somewhere between, based on the Keller well, that the lake would be, what was it,
60 meters east to west.
60 east to west, and
yeah.
How deep?
I think we might have guessed 50 meters deep, more or less, something like that.
Let's just pull that up.
Yeah, 50 meters deep.
50 meters deep.
Yeah. So if we use, it was 90 meters across east to west is what is our closest measure. Let's say it's 90 east to west on September 2nd. Like maybe we can round that. We'll round it to 100 to make it easy, right? But it might actually be 95 or something like that, east to west. And it might get to 260. So it might get to be 2.5 times bigger east to west than that is now.
Right.
That's more or less what we're looking at, right? So it's still a long way down and far away, so it's hard to really say.
Yeah.
And
USGS their estimate was even deeper than this.
Right.
Theirs was around 200 feet deep.
Yeah, 68 or 72 meters deep, I believe, was their actual number, right? Right. Yeah, and so this image on the screen now is actually just done from pixel analysis from this actual image you see on the screen in front of you. So an error of 20 meters is that's well within the lack of precision of this technique, right? So definitely believe that 68 and 72, and that may actually imply 300 meters across, something like that in the end. It may end up being 3 times wider than it is now.
Definitely interesting how this thing, and it should eventually hit some kind of equilibrium, basically, and we'll see it slow, and then the water level will kind of just stop rising in this scenario. Right. And it would be one other thing. It would be nowhere near the edge of the crater rim, the collapse pit. It would just be the very little bottom of it when you look at the big scale of things.
It's still going to look small.
It'll be pretty big.
It's going to be big, but it's still going to look small from as far away as we're going to be, or from where the camera's going to be looking at this thing. It's still going to look small.
And nobody is getting down there and back up to it, like without a helicopter, harnesses, and that kind of stuff. And even then, no water sample has been pulled yet. No. Still some talk about how to do it and stuff like that, and they're being careful. There's a bunch of different considerations that they're having. Mm-hmm. But yeah, it's the water sample itself would really help us tell a lot. Basically the age of the water would be the main thing right away. How old is this water?
Yeah, for sure. I'm sure that someone at HBO is obsessed with this right now. At least
definitely.
One person. So I'm sure that we'll hear about it as soon as they're able to do it. The other interesting thing to me is, talking about the filling rate, right? Even without looking at any kind of variations in what we can tell, we know it's been 2 months. It's been not quite 2 months, right, of water filling it up, and it's 100 meters wide at this point. So how long might this take to actually keep filling? How long is this going to keep going?
Right.
It could go for many, many more months.
Definitely.
Many, many, many more months, in fact.
Especially with some of the early estimates seem to be a little bit fast.
Mm-hmm.
For how much the water was coming in, and as it's been more, we've had more time, it seems to get a little bit more refined, and that rate is about a meter a week, a little less. So, and at one point we're thinking like a foot a day, right? So that would have been different measurements, but
let's go with a meter a week. Can we do it that way?
Do a meter a week to keep it simple. At
meter
that
a week,
point.
4 meters a month.
4 meters a month, and we're at say 40 meters right now. No, not 40 meters, 40 feet deep. So like
that's
20 meters, like
15, 13 meters.
yeah, 15 meters, we'll call it deep. And we have 50 meters total, so we have 35 to go.
Mm-hmm.
So we're about a year out.
Yeah, if it was 4 meters a month, 12 months is 48, right?
Yeah. Then
10 months is
and
40.
we'd have to assume also that when it gets towards
36.
equilibrium, it slows down.
Right.
It doesn't just, pop, 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 stop. It goes
Right.
up and then slows type of thing at the end.
So order of magnitude calculation, back of the envelope, 9 months.
Yeah. 9 months to a year, basically.
9 times 4, 36.
Yeah.
36 plus 14, 50. That's very back of the hand order of magnitude. But that's about, maybe it'll take 7 months. Maybe it'll take 11 months. But we're
Right.
talking about that's the range. It's not going to
Yeah.
take 1 month
Or 5 years.
or 5 years.
Right.
Yeah.
We'll know what this lake is going to look like eventually, and it won't have to wait forever for this. In terms of geologic time, it's a blink of the eye. Its existence entirely too.
Yeah.
Because
But
one thing we've talked about Kilauea, there not being any activity. We don't expect magma to come back now soon, but it is going to come back. And that lake is going to go away.
Yeah.
These are just things that will happen.
Yeah, at some point, that lake's going to be nothing to get in the way of magma.
Right.
It's just going to be
A little blip.
just a casualty.
Right. Let's see if we got any questions going. Can it grow as big as the Crater Lake in Oregon? Nope. Very unlikely.
Yeah. Crater Lake in Oregon is it's different in a sense of its structure, right? Like the biggest obvious difference is that Crater Lake in Oregon, the water is perched above the ground, right? Like the crater is on a mountain that's above the ground and it's kind of sticking up like that. And here we're set in, right? And we have a similar structure. It just looks very different because of the shape of the shield as opposed to the actual stratovolcano.
Right.
But first that's part one. Stratovolcanoes are smaller in area, right? So like it's steeper at the surface. So you have like a smaller kind of perched water pond within that area, and then a larger regional water table is farther off as well.
Right.
So that's happening at Kilauea as well, but it's not just the summit; it's the summit and all the rift zones and like that structure kind of spread all the way out, and it's really spread out and larger.
Once you go down to that depth, you just hit water, like on Kilauea, and it just so happens Holly Mau collapsed that far, so now we can see water.
Right.
Was the water there before? Yeah, it's been there, and during every big eruption, East Rift Zone eruption, it also involves water in some degree. It comes back up through the water table.
Right. Yeah.
The intrusion does. So there's always water involved in this thing.
Yeah. I mean, it is similar in a sense that they both have water that's kind of stuck above the regional ground above it because of volcanic barriers that exist.
Right, exactly.
That's the similarity of it. But beyond that, the actual shape and size and dimensions, all that make it so it's not going to be the same as Crater Lake. That's probably the easiest way to put it.
All right, so we've gone through basically everything I think I wanted to get through.
Any more questions? Anyone give me a chance to ask any more questions?
What's the chance of geysers forming?
That's interesting. I mean, I really have no idea. I for a long time, I've said that the same hydrothermal, right, hot water circulation processes, are possible under Kilauea as somewhere like Yellowstone, where you actually can go and visit geysers. The difference has always been, to me, the position of the water table in relation to those events, right? So like in something like Yellowstone, you actually are walking 2 feet above the water table, and that's where the mud is bubbling up.
Yeah.
Right, so the gas is bubbling through the water table, and it's just right there. So if you were standing at the level of this lake, you might have eventually similar kind of bubbling thing that happen on there. But I don't know. It all depends on the dynamics of the hydrothermal system, the faults that the gas and water is moving through, blockages that occur. Those occur based on pressure of the steam and how all that has to kind of
the other thing I would think
equilibrate first. Yeah.
The one important side note on that would be the type of rock that's there as well. Porous basalt versus clay and whatever at the yellow. I'm not even sure what it is there, but it's like it holds water. It can create seals and stuff like that temporarily. Create enough pressure, blow the seal,